This is a talk giving some current perspectives on the problem of quantum black holes. For starters, it seems to me likely that the problem of quantum black holes gives us a guide to the new principles of quantum gravity, whatever they are, and so is very important from that perspective, and also may lead to possible observational signatures. There are numerous perspectives on this problem, and for example, there's been a lot of recent focus on entropy calculations. But of course, entropies are just one diagnostic, and I'm going to instead suggest that we think about the problem at a more basic level, connecting with the information theory perspective, and this will also focus on certain questions that may be important for the structure of quantum gravity. And I'll start by stating what I'll call a black hole theorem in quotes, and this should be taken in the spirit of the Coleman-Mandula theorem, where the important thing there was the loophole through which supersymmetry came into the game. And of course, here too, the important thing is probably the loophole. So a first statement of the theorem: if a black hole is a subsystem, if distinct black hole states have identical exterior evolution, and if black holes disappear at the end of evolution, then this violates quantum mechanics, specifically unitary evolution. This is a statement or set of statements which could apply to other subsystems of other quantum systems, but let's focus on the situation for black holes. So first, subsystems. In much of the literature, subsystems are described in terms of factorization of the Hilbert space into a product. But in local quantum field theory, for example, we see that's not quite the correct description. And so instead, let's think about that description as an example. So here is a space-time of a black hole in the Penrose or Eddington-Finkelstein representation. Let's take a slice through the space-time and think about the state on that slice. And there are independent excitations or descriptions of the parts of the state corresponding to the internal black hole part and the external environment part. So we can write the state in this form. At a more formal level, in local quantum field theory, we might describe this in terms of commuting subalgebras of the full algebra of observables. And that provides a way of making this a little bit more systematic in that context. I think this is an important point, which we're going to return to shortly. In local quantum field theory and other quantum systems, subsystem structure really is hardwired at the beginning and is part of the very basic description. So the question is, in quantum gravity, what plays an analogous role? Secondly, distinct black hole states have identical exterior evolution. So let's consider a sequence of slices. Here, two are drawn. And if we consider an excitation interior to the black hole, so we could have one or the other, say, state or part of the state here, then those excitations in the local quantum field theory description stay within the light cone and go into R equals 0. So if we describe the evolution law, which you can write down quite explicitly for local quantum field theory, you see that the environment part of the state is independent of the initial excitation here. So that's very concretely realized in local quantum field theory and has been the subject of some recent study at an explicit level, including some additional generalization to D dimensions with a UCSB student that's in preparation. One way of characterizing this property is to trace over, or imagine tracing over, the internal degrees of freedom of the black hole to give a density matrix, which will be independent of the internal state. But that's rather cutoff dependent. Another way of stating this property is to say that for all observables in the environment, if you look at an expectation value of such an observable, that's independent of the, say, initial state inside the black hole. So this is where we're encoding the locality principle of local quantum field theory. Here we've ignored gravitational back reaction in describing this story, but of course we could go one step further and semi-classically include that, like was done in the two-dimensional models, say the CGHS model, and the same structure still holds. And this serves as an example of what we believe is likely to be, or at least we might believe is likely to be the more general structure. Finally, a black hole disappears at the end of evolution. Well, let's suppose that the evolution law is such that a state like we've described turns into a state of the environment, say just outgoing particles, that's independent of the internal states of the black hole. If that happens, clearly that's many to one evolution. Therefore, it's non-unitary and violates is contradictory to quantum evolution. There are different diagnostics of that. For example, we could take this set of states and entangle them with an auxiliary system that naturally happens with the early Hawking radiation. And you could compute, say, the entropy of entanglement. And initially it's non-zero. And if this kind of evolution law holds, then it transitions to zero. And that's one way of exhibiting the violation of quantum mechanics. So to evade this chain of reasoning, we need to violate one or more of these assumptions. And again, like with the Coleman-Mandula theorem, the important thing is likely the loophole in the reasoning. There are various proposed outs. This has been discussed, of course, a lot over time. A good test question, or set of test questions, I should say, for your favorite proposal is, how does that explicitly differ from local quantum field theory evolution, which gives the Hawking story? Again, we've increasingly have an increasingly detailed description of that. How does your proposal alter these basic assumptions? And what other assumptions are required? So different scenarios, some older ones first. Microscopic remnants would correspond to something being left behind by the black hole, so they violate assumption 3. And of course, introduce other rather severe problems, for example, infinite production of those remnants, and more is described here. Another general scenario that's been described quite some time ago is that a black hole at some point in its evolution, while it's still big as compared to the Planck scale, transitions into a new kind of object that is no longer a black hole. Let's just generically call it a massive remnant. And examples would be, say, fuzzballs, firewalls, gravistars, Planck stars. Various cases have been given. And clearly this would modify both the picture of black holes as subsystems and also the description of their evolution. And typically this kind of scenario requires additional assumptions, which may be rather problematic. There's the ER equals EPR proposal, which is sort of suggesting a different subsystem identification, but there's a question of how that systematically works. And there are various other scenarios. One that I want to focus on has been quite popular recently, that of replica wormholes. And here a starting point is the following diagram where we have the increasing entanglement entropy of the outgoing radiation with the internal states of the black hole in, say, Hawking's description, and the falling Bekenstein-Hawking entropy. And Page was the first one to clearly enunciate in print that if we have unitary evolution where the black hole disappears, then the actual entropy of entanglement should follow a curve that's the lower of the two. This replica wormhole story sort of gives a formal prescription for how to arrive at this result from a formal Euclidean path integral argument. But there's a real set of questions here about how we relate this to the standard quantum mechanical language of states and amplitudes, or in fact, does it represent some modification of quantum mechanical rules? And that's briefly discussed in this paper. But if it does fit within the framework of states and amplitudes in standard quantum mechanics, the best candidate for an explanation is the proposed connection to emission of baby universes. And here's a rough picture that you might have some piece of the interior of the black hole that branches off and forms a new baby universe through a process that's related to space-time wormholes. So this has been explored by Meroff and Maxfield and various others. Now that seems like a modification of the subsystem structure. Information is going off into the baby universe state. But in a general approach, at least in an approximation where you neglect interactions of baby universes, one can argue that something else appears to be happening. And this goes back to work of Coleman and myself and Strominger. The interactions of the baby universes with our universe can be described by a correction to the Hamiltonian. Here we have baby universe annihilation or creation operators, coupled to operators that describe the effect of the baby universe on our part of the universe. And then if we work in states where we diagonalize these operators, these are called alpha vacua, then effectively we just have a correction to the Hamiltonian, which is some new coupling constant times the operator describing the emission. If those operators are localized inside a black hole, it's hard to see how that helps, because then you're back into the situation where you just have some other couplings, but you have the basic assumptions of the black hole theorem still in force, and this doesn't clearly offer you a way out. On the other hand, there is another possibility that these operators are non-local on scales of order the event horizon size are larger, corresponding to emission of very big baby universes, and that could violate assumption 2. Namely, that could give a way for outside evolution to depend on the black hole state, effectively would yield non-local interactions. I'll return to this in more generality shortly. Or is there some other interpretation, or is this approximation not valid? Those are good questions. What we really need in this story is a clear explanation of what is going on. But I'm going to return to a more general discussion and go back to the assumptions and ask the question, how much structure really needs to be introduced? Is there some way of solving the problem with a less drastic modification of the physics? And first, let's focus on this question of what is a subsystem. That's an important basic concept for any quantum system. In finite or locally finite, like lattice systems, we describe subsystems in terms of a product structure for the Hilbert space, and that captures the fact that a measurement, say, in one factor is independent of the part of the state in another factor. In local quantum field theory, that's, again, not quite the right structure due to the type 3 property. Instead, we describe things in terms of composing some subalgebras of the algebra of observables. There are nice reviews on this, for example, Hogg's book. And let me just illustrate with a simple example. So we can take a neighborhood and consider, say, the vacuum, and act on that with a state where we integrate a source that has compact support restricted to that neighborhood against, say, a scalar field. And so we form a state like this. And the essential point, or one of the essential points, is if we, say, measure the scalar field outside the neighborhood, as described by, say, looking at this expectation value, that measurement is independent of whatever we've created in the neighborhood. So Hawking evolution respects this property. This is what's constraining the information escape, and is one way of, is part of the statement of locality. But the problem is in gravity, a field phi of x is not gauge invariant. It doesn't commute with the constraints. Likewise, the state that we've described is not annihilated by the constraints. And here we can write the constraints in terms of the stress tensor and the Einstein tensor, looking at, of course, the zero mu components, thinking about things in terms of sort of an effective description of quantum GR. The basic physics here is that a particle is inseparable from its gravitational field. And so we have to account for that. And we can do so by solving the constraints and constructing what is known as the gravitational dressing. That can be done perturbatively. Let's perturb about a background, and here is the quantum metric perturbation. Kappa is essentially the square root of Newton's constant. And so, for example, we can take this state we described and promote it into a dress state in terms of a dressed operator as follows. So the dressed, say, state is gotten by taking certain exponential or certain functionals of the metric perturbation. There are actually various choices here, integrated against the stress tensor, and then we exponentiate that. That gives the leading order dressing. And likewise, when we talk about operators and their dressing, we conjugate by such construction. And this has been explicitly spelled out in these references, also recently studied in this reference. And these operators are essentially creating the gravitational part of the operator that dresses it and runs off to infinity. Once you've done that, two of these operators corresponding to excitations at, say, space-like separations no longer commute because the dressing part of the operators collide here, as it is explicitly checked. And likewise, for example, if we try to measure the metric perturbation outside the neighborhood, we get something that depends on the fact that we've created a non-trivial state here. So there's a question of, in what sense does information localize in quantum gravity? What is a subsystem? And that looks like a key structural question for quantum gravity. So some results on that. First, the perturbative dressings, well, again, there's a choice of dressings. There's a fair amount of latitude there. The perturbative dressings can be chosen so that, say, the endpoint function of the metric perturbation outside the neighborhood depends only on the Poincare charges of the stuff inside. That's been shown in these references. And that, by the way, suggests a limited role for the soft hair story, because basically the soft hair can be decorrelated with whatever's in the neighborhood. It only has to capture the moments of the Poincare charges. On the other hand, there are observables which can see the excitations from afar. The argument for this comes from the expression for the translation generators, where they're written in terms of the ADM expressions, which depend just on the metric perturbation at infinity, plus the constraints. So if we've solved the constraints, then we just have the term at infinity. And Maroff, in fact, suggested this is a candidate explanation for holography. So for example, we can take an excitation or operator in this neighborhood and think about mapping it into an excitation, say, on the boundary of ADS through propagation, and then using the boundary Hamiltonian to translate it back to an excitation or operator back here, thus providing the holographic map. In fact, there's a simpler story, I think, which Donnelly and I stated, that you can just use the translation generators in a simpler form to just take the state and effectively translate it out to large distances or near infinity, where you can make an observation. So formally, if we have a dress state, we can see that there's a non-trivial excitation there through operators that live out, say, at infinity. We take the dress state, we perform a translation, and then we act on the state with an operator that, say, measures the structure of the excitation out at the boundary. And that will depend on the form of this excitation. That's the basic argument. So that suggests that information is delocalized in gravity. Some notes, however. First, we need to have a solution of the constraints for this to work. Moreover, in general, it has to be a non-perturbative solution. One way of seeing that is you could try to apply this in the general circumstance, including, for example, if you have excitations inside a black hole, maybe you have sources coupled to two different scalar fields and you want to tell the difference. And to apply this argument, clearly you have to be able to have non-perturbative control over the solution of the constraints to relate this to observables at infinity. Also, just without black holes, you need a large translation, basically an infinite translation, to make this work. And that's also involves a non-perturbative statement. It's been suggested that this story extends to perturbative availability of information, but the terms in the examples given are actually exponentially small, so that remains under question. So bottom line is, taking into account these limitations, there's an interesting story with the dressing, but it's not clear that that's enough to resolve the problem and that that's sufficient to imprint information outside a black hole. And moreover, to find this dressing, you need to solve the constraints, which means solving the problem of quantum evolution of black holes. So there's a sort of circularity. But let's go back to our assumptions. And now I've added quantum mechanics as one of those. And so one way of reading the conflict of these statements is quantum evolution plus disappearance mean that either one or two or both fail. So that's sort of a non-locality theorem. That's version 2 of our theorem. We have a departure from the local quantum field theory paradigm. But I'm going to take the point of view that, or at least investigate the possibility that we do have a suitable definition of subsystems, at least to a good enough approximation. So we can basically think of the Hilbert space as factorizing or the state having the structure that I've described. If that's the case, then if we examine this conflict, we see that quantum mechanics plus the existence of subsystems plus disappearance of the black hole at the end of evolution imply that distinct black hole states don't have identical exterior evolution. So that's version 3 of the theorem. And that means that there must be some kind of new black hole state dependent interactions that are responsible for this. This is a story I've been investigating in a series of papers, some of which are listed here. Such black hole state dependent interactions clearly have to violate the semi-classical locality. What we can do is explore these in a principled parameterization of ignorance. Parameterizations of ignorance can be very powerful. You can in fact think of in basically discovering field theory this way. So an overview is in this paper here. We start out with a state in the form we've described. There needs to be some correction to the local quantum field theory evolution that effectively transfers the information. The simplest possible form of that is some operator. Let's consider all operators that act on the black hole states times corresponding operators that act on the environment part of the state. Now, if the environment is pretty well described by local quantum field theory to a very good approximation, we should be able to build these operators out acting on the environment basically from local quantum field theory operators. Some other points to guide our description of these interactions. First, they need to act on the outside state, outside the horizon. So they need to act on scales at least of order the horizon size. And here we can compare, by the way, the wormhole discussion that we gave earlier. That's sort of a natural scale. And in fact, it's natural that these operators act on scales of order the event horizon size outside the event horizon rather than say just a Planck length outside the horizon. And that avoids rather unnatural things like firewalls. Another argument for that is really that's where the black hole radiation is produced. There are various ways of explaining that or exhibiting that in this sort of quantum atmosphere surrounding a black hole. So that's a natural place to look for a solution to the problem. Another point is that it's a reasonable hypothesis that these couplings are universal to all different fields. One reason is to maintain the, at least to a good approximation, the thermal description of black hole evolution. There are also Gedanken experiments involving black hole mining, which suggests this should be true. And there's just the general property of the universality of gravity. So we can satisfy those conditions with an expression that looks like this, where we just couple to the stress tensor. Then we have what are effectively form factors that have support on scales of order the event horizon size coupled to the generic operator. We can reorganize this expression by combining the operators and the form factors into something that looks like a black hole state dependent metric perturbation integrated against the stress tensor. And then there's one additional important constraint that these interactions have a job to do. They have to undo the damage done by the Hawking radiation, so to speak. They must transfer information or entanglement at a certain rate, which is 1 qubit per light crossing time in order of magnitude. One way of achieving that is if these effective metric perturbations have a typical size in a typical black hole state of order 1, and again are varying on scales of order r. That's sufficient, clearly, to transfer this much information and corresponds to what I'll call a strong or coherent scenario, because, basically that means order 1 perturbations to the metric. And that is interesting if those perturbations reach out to the outside of the horizon, because that's a region which is being probed by event horizon telescope observations and possibly could lead to visible signatures. For example, time-dependent distortion. So some of that story has been discussed here. And in fact, the very beautiful image from M87 is essentially providing bounds on the scenario if you look at it carefully. But there's a question of, do the couplings really, or the effective metric perturbations really have to be that large? And this touches on a very general problem, how to understand the information transport rate between subsystems for given couplings between the subsystems. There's a conjecture here and some tests of it, which basically follow the logic I'm about to describe, that basically you can think of transfer of information as the rate of transfer of information as a lot like the rate of a transition to occur, where say you have two systems like an atom and its environment interacting, and the atom decays by creating an excitation in the environment. So that's well described by Fermi's golden rule. We have a rate which is given by 2 pi times the density of final states times the matrix element squared of the perturbation. In the density of final states, we include the final black hole states. So that's a very large number, exponentially large. And that tells us that this interaction could be exponentially small and still get this rate of order 1 over r. And that corresponds, in fact, to having a metric perturbation in a typical black hole state, which is exponentially small. So I'll call this the weak or incoherent scenario. And of course, that's going to be harder to see with, say, event horizon telescope observations. But you can get important modifications to gravitational wave scattering from a black hole from the same kind of analysis. Now we just consider transitions where we have an initial and final state of our scattered gravitational wave. And the same parametric dependence holds. You have an enhancement here from the black hole final states, and you can have a small matrix element and get an order 1 transition rate at, say, changes or at shifts of momentum transfers of order 1 over r. And so that suggests that we can get important modifications to absorption or reflection at these wavelengths. And of course, LIGO and Virgo and other gravitational wave detections or ways of other gravitational wave observatories are effectively observing signals with an important component that involves wavelengths of order of this size. So that's a story being explored. So just to finish and summarize, the basic statements that quantum mechanics holds, a black hole is a subsystem, and distinct black hole states have identical exterior evolution, and finally a black hole disappears at the end of that evolution. Those statements are inconsistent. It's helpful to understand how a given scenario evades this. And an important question in my mind is, can we do so with minimal new assumptions without a lot of dramatic new structure? This does touch on a question that I think is important in gravity. What is a subsystem? How did we describe it? That seems like that may be part of the basic structure of quantum gravity. We have some results on that, but also remaining puzzles. Plausibly, though, we have an approximate description of subsystems, and I've investigated that possibility. And so finally stated the version of the theorem that says that if quantum mechanics does hold, if you do have subsystems to a good enough approximation, and if black holes disappear, then there must be new interactions between the black hole and its environment, which are non-local with respect to the semi-classical description, which we can parameterize in a principled way, and which lead to possible observational consequences. For example, via event horizon telescope observations or gravitational wave detection. So I'll stop there.